Okay, we're ready? Okay, so, yeah, she's on the phone somewhere. I believe the last lecture where I left off was saying that if I gave you like a fourth order transfer function, and I said here if we had an input that had like 2 or 3 different sinusoids in it, that if you were to use Z-transforms to calculate the output, you'd wind up with something like an 11th order Z-transform that you would have to partial fraction expand, and I said that's no fun.
Yeah.
Is that where I quit?
Yeah.
Okay, good, because today we're going to start with the discrete time Fourier transform, and that is actually a way to approach that problem. Now, it's not quite as robust in the sense that the DTFT will not give you transient information, okay? And if transient information is important to you, then this won't work. This is not sufficient. And I'm going to go ahead and abbreviate DTFT. Not to be confused with the discrete Fourier transform, which is where we'll go next, the DFT. That's something totally different. Now, the definition, I'll use the notation x of e to the j omega sum from n is negative infinity to infinity of x of n e to the negative j omega n. And if you notice, that can be gotten directly from the Z-transform if you replace Z by e to the j omega. A problem. If you're looking online or you're looking in a lot of even signal processing textbooks, they will use this notation. Please don't write this notation. They'll write that as x of omega. Okay? Here's the problem with that. That would imply that that'd be the same as x of z, just replace z by omega. And that is not right at all. When I use, it's not as neat and concise, but when I use x of e to the j omega, that's just x of z with z replaced by e to the j omega. Now, what does this mean? If z is e to the j omega, let's refresh our memories. With Laplace transforms, we took s and replaced it by just j omega, and that converted Laplace transforms to who? Fourier transforms? Okay, by doing what? In the Laplace domain, here we have the S-plane, there's sigma, there's j omega. So Fourier transform is just Laplace transform on the j omega axis, right? That's what S equals j omega means. Well, what does z equals e to the j omega mean? It means that if this is the z-plane, e to the j omega, remember that's a complex function. And it has, more specifically, it's written as a complex number. Its magnitude is 1, what's out front, and its phase is just omega. So what does that mean? If z is e to the j omega, its magnitude is 1 and its phase is omega. What does magnitude equal 1 mean? We know what that is.
It's on the x-axis.
Magnitude? Radius? What is it? Go ahead.
It's the radius.
Radius is 1, so what is that? Unit circle. Right, it's unit circle. So that's just the z-trans. So when I say x of z evaluated at z is e to the j omega, that's just a unit circle. So let's see, unit circle. And if you plug in a few values, Omega is 0, means that z is e to the j 0 is 1. So this point right here is z equals 1, which is where omega is 0. What about this point over here? Right there. That's where z is. Where does that intersect on the negative real axis? You all know this? Z is negative 1. And that's when omega is pi. So omega equals pi gives you a z of negative 1. Is that correct? E to the j pi, cosine pi plus j sine pi. Sine pi is 0. Cosine of pi is negative 1. Okay? And up here, this would be omega is pi over 2. So you would have e to the j pi over 2 is cosine pi over 2. What's that? Plus j sine pi over 2. Cosine pi over 2? 0. Okay. Sine pi over 2 is? Sine 90 degrees. 1. So that's just j. Up there, that's j. That intersects at the imaginary axis at j. This intersection point down here is where omega is negative pi over 2, or omega is 3 pi over 2, either one, the same place, same location. So now, we're going to talk about Fourier transform of signals and of systems. So if I define this, h of e to the j omega, sum, n negative infinity to infinity, h of n, e to the negative j omega n, which is just h of z, evaluate z as e to the j omega. Can I do that? Sure can. I can define anything I want to. It's just a question of whether it's useful. And this is actually useful. This is what we're going to call the system's frequency response. And the frequency response of the system. So, do we know what frequency response means? How the system responds to different frequencies. That's a good circular definition. But we do know what it means. It means that if x of n is a1 cosine omega 1n plus a2 cosine of omega 2n, then the output, y of n, will be what happens. We've got a signal that is made up of two sinusoids going through an LTI system. What happens to it? How does it get changed? What changes? Tell me.
Repeat the question.
Okay. We have an LTI system, and we have sinusoids going through it. How do they get changed when they go through it? What are the three parameters for sinusoid?
Oscillating.
Amplitude, frequency, phase. What changes as it goes through the system? Amplitude? Yep. Frequency? Nope. Phase? Yes? All right. It changes this way. A1, magnitude h of e to the j omega 1 times cosine of omega 1n plus angle h of e to the j omega 1 plus, same terms except with a 2 subscript, a2 magnitude h of e to the j omega 2 cosine omega 2n plus angle h of e to the j omega 2. Right? So do y'all see the factors where it changes in amplitude? They change in amplitude by this, magnitude of h, and they change in phase by the angle of h. Magnitude, h of e to the j omega, is called the gain response of the system. Angle h of e to the j omega is the phase response of the system. And so as the sinusoids go through, they get changed in magnitude, they get changed in phase, but they do not get changed in frequency. So what does that mean? You will never get any frequencies. Finish the statement. You will never get any frequencies out that didn't go in. It won't create new frequencies. Obvious? Frequencies omega 1 and omega 2 went in. Frequencies omega 1 and omega 2 came out. No other frequencies. It changed their amplitudes. It changed their phases, but it didn't change the frequencies. And so, we're going to talk about how to calculate this gain in phase response. In other words, the frequency response of the system. But before I actually go into calculating it, I would like to show you how to estimate the gain in phase response. No, in particular, the gain response. We're not going to deal with the phase response right now. So, if I have a transfer function for a system. Am I moving a little fast? Okay. I have a transfer function for a system, and let's say it has a gain factor, k. Now, k is just a constant out front, and then I have some zeros, z minus z sub a, z minus z sub b, and I may have more. And by the way, those zeros can be real or complex. It actually doesn't make any difference. Denominator, z minus z1, z minus z2, and there might be others. So what would you say? It has zeros at za, zb, etc. It has poles at z1, z2, etc. So now, I'm going to find the frequency response, k. That would be e to the j omega minus z sub a. Remember, z sub a is a constant. And e to the j omega minus z sub b, etc. Denominator, e to the j omega minus z1, e to the j omega minus z2, etc. And there could be many terms in the numerator and denominator. And by the way, some of those terms could be repeated. Okay, in other words, Z1 and Z2 could be equal, meaning you would have a double pole. Doesn't make any difference. So, what I'm interested in right now is, let's take the magnitude of that. Magnitude, magnitude, magnitude. Why? Because I'm calculating the gain. Good? Now, magnitude of k, in some cases, k might actually be negative, but it will not be complex. So, that's just absolute value of k. You all know we use the term absolute value for real numbers, magnitude for complex numbers. Pythagorean theorem. Okay, so we'll get magnitude e to the j omega minus z sub a, magnitude, excuse me, e to the j omega minus z sub b, etc. Denominator, magnitude e to the j omega minus z1, magnitude e to the j omega minus z2, etc. Now it's time to draw a picture. Let's draw a picture and talk about a geometric interpretation of that equation. So, we all agreed that when we replace z by e to the j omega, we're going from the entire z-plane down to just the unit circle. down the unit circle. Okay, let's say we have a couple of poles, and let's say the poles are here and here, and I'm not going to tell you exactly what the locations are, but they're inside the unit circle. That's a good thing, right? Stable causal filter. And they're over here on the right, in the right half plane. Now remember, this is not the Laplace domain, so right half plane doesn't have any implications about stability. Inside the unit circle does. And I'm going to say that there is a 0 right there, and that's all. A 0 exactly at -1. So, I would like to plot magnitude h of e to the j omega versus omega as we go from 0 to pi. Now, so omega 0, you remember, starts right here, and then we're going to run around that circle, and I'm at some particular frequency. That frequency right there, that point is e to the j omega, right? And by the way, that means that the frequency I'm at is right there. That's omega, that's the angle, the phase. Absolute value of k, just a number, right? It's in all the terms. So let's just say k is 1, leave it, forget it. All right? What if k is not 1? Well, it's just going to multiply the whole expression. That's it. No big deal. What is this? Now, in this case, since I have 2 poles and 1 0, I'll just erase that to make this specific to this particular problem. What is that? E to the j omega minus z sub a. That is this, and I'll draw it in blue. E to the j omega minus z sub a is that vector, and when I take the magnitude of that vector, that's finding the length of it. What is that? The length of that could be called the distance from there to there. Right? So this expression right here, and since I drew it in blue, this will be the distance from e to the j omega, that's a point on the unit circle, to the 0. Would you agree with that? Subtract the 2 and take the magnitude. You remember back in like 2nd grade when you were dealing with real numbers and you were told the absolute value, oh, you weren't a baby, the absolute value of 3 minus 2 represents the distance between 2 and 3. And you did absolute value, because what if you did it in the opposite order? Absolute value of 2 minus 3 would be 1, the distance between them. Well, now I'm not saying absolute value, I'm saying magnitude, because I'm talking about distance out in the plane. And that minus that, and take the magnitude, that's just the Pythagorean distance between the 0 and wherever we are on the unit circle. Okay, now the next one. What about this one? E to the j omega minus z1. That is, z1 is a pole? Pole? Okay, so that is this distance. When I take the magnitude, it's a distance. And then, I got just enough colors here. Red, that would be the distance there. These are interchangeable, it wouldn't make any difference which order I did them. So what have I got there? I have an expression that looks like this. Absolute value of k, capital pi for product. You know we're used to using capital sigma for sum. Capital pi is used for product. Of distances, 2 zeros over product of distances to the poles. Now, notice that we only had one zero, so there's no product up there. It's just distance to that zero over distances to the poles. Do you see how I got that? See all the steps in between? So what I'm going to do is this. I'm going to start off at 0 right there on the real axis, and then I'm going to run around the unit circle all the way around to pi. And for every frequency, as I move around, the frequency is that angle. As I move around there, I am going to calculate distances to the poles and to the 0, and do that calculation over there. And I said, just like KB1. What does that mean? Starting off over here at omega is 0. Describe in words where I am. What am I close to? If I were to look around me, what would I see? What am I close to? Close to a pole? Not too far from another pole? Pretty far from the 0, right? Now, when I say pretty far, I mean in a relative sense. Relative to what? Well, I'm going to be going around that, and I'm going to get close to that 0 eventually, but right now I'm very far from it. Agreed? Okay, so I'm close to 2 poles, and I'm real far from the 0. So what does that mean? That means the distance to the 0 is big. Okay, everything is relative now because I haven't told you where the locations of the poles and zeros are. I haven't told you what K is. I said just assume 1. Distance to 0 is big. What about distances to the poles?
Very
Small. I said close to the poles. Close to means the distance is small. So what does that mean? If these distances in the denominator are small, what happens when you take the reciprocal? You get 1 over small numbers because you're close. What does that give you? Big numbers.
Number.
Right? Big numbers.
It's on my hand.
Okay, so we start off over here, we're close to the poles. Close to the poles means these distances are small. They're in the denominator, which means 1 over the distance is going to be big. Now, as I go around here, what happens? What happens to the distances to the poles as I move? Distance increases, that's in the denominator, so it gets, and by the way, as I move around here, this distance will start to get significantly less. And so, that's right, starts off up there, and then falls off, and by the way, when I get to pi, I see it goes to 0.
Yes.
Oh, it touches.
It does, that's right. When you hit the 0 right there, because, and remember the 0 has nothing to do with stability, and so I'm all right to put it right on the unit circle. Don't want to do that to the poles, but I can with the 0. Which means the distance to the 0 actually gets 0, to be 0. And so, I wind up with what looks like remember that's the gain I just plotted. What kind of filter does that look like?
You should keep going around, right?
Yeah, we'll do that in just a second.
Because then it'd be a notch, but right now.
No,
Well, if you
Careful.
keep going around, wouldn't it start increasing then?
okay.
As an
It's
increase?
going to be, since you're going to make me do it now,
Increase.
it's going to be a mirror image.
Yeah.
Okay, there's 2 pi, but remember 2 pi, we're right back to 0.
Yes.
Here's your highest frequency. Because remember,
2, 5.
once you go beyond there, you're heading back towards 0 again. That's your highest frequency because this is omega equals 0. That's DC. This is the farthest you get from DC on the unit circle. So there's your highest frequency. Okay, now, It's low at high frequencies, it's high at low frequencies. Did I say that right? Yeah. Okay, what have we got? Low pass? Okay, we've got a low pass filter.
Yeah.
All right? So, now, I'm going to give you some numbers to work with. And then, I'm going to let MATLAB work with those numbers, because I'm not working with complex numbers.
People say you love MATLAB.
Oh yeah, I love
Yeah,
MATLAB.
at my work, they said, have to panic. MATLAB.
Okay, so let's say a specific example. Let's let K be 1, that'll make it easy. No, let's put a K in here, actually. And then I said we had a 0 at -1, so Z plus 1. Denominator, Z minus, let's just say 0.9 and Z minus 0.8. Right? Does that agree with what we have over there? Okay. So, I want to throw in another Z, just for fun, because this will make life work out much better. I put a Z in the numerator. When I put that Z in the numerator, what does that add to that drawing over there? 0? Where at? 0 at 0. Okay? I claim that doesn't have any effect on the gain response. Anybody believe me? Why? Why does that not have any effect? Because now I also have to calculate the distance to that 0. What?
It's always going to be the
Zero.
same distance though, it's never going to change.
That's right. A 0 or a pole at the origin has no effect on the gain response because by definition, as you go around the unit circle, the distance is always 1. The fact that it's 1 is not important. The fact that it's constant is all that we need. So it's going to make the math work out a little easier later. So I'm going to put that Z up there. Would you agree that if I wanted to, I could write this as K times 1 plus Z to the minus 1? I need to multiply out that denominator. That's Z squared minus 1.7Z plus 0.72. Okay, so this could be written as 1 minus 1.7 Z to the minus 1 plus 0.72 Z to the minus 2. I just multiply by Z minus 2 over Z minus 2.
Okay.
Okay, there's going to be a time I'll need that. Let's just assume for now that K equals 1. All right. Down comes the screen. Now we use MATLAB. The whole point of DSP is you don't do DSP by hand. While that warms up, I'll be putting in the coefficients. My numerator is 1 and 1, right? My denominator is 1, negative 1.7, and positive 0.72. You all can watch the screen. Keep an eye if I make any mistakes. I'm trying to talk and type, please, at the same time. All right. Are we ready? There. Okay, frequency response. Freq. But if I do frequency, F-R-E-Q, this is a command built into MATLAB. If I do frequency, numerator, denominator, it's going to treat it as if it's a Laplace transform, transfer function, a continuous transfer function. It's not. It's a discrete transfer function. We want it to plug in e to the j omega. Freq, numerator, denominator, meaning frequency response from a Z transform. And so, there's your plot. And it thankfully gives me magnitude and phase responses. What's it look like to you? Magnitude's on top, phase bottom. Ignore the phase for now. Looks like that, doesn't it? And by the way, it only goes, notice this frequency here, this really doesn't have any units. It's divided by pi. So when it goes from 0 to 1, that's actually going from 0 to pi. But it's easier broken up this way. It's easier to see. Pi over 4 is there. Pi over 2 is there. Okay? Keeps that horizontal frequency axis fairly neat. Low pass filter, right? It's fairly common, I'm sure you all know this, for us to normalize filters so that their peak gain is 1. What's peak gain up here? What's peak gain? Read it. Gain at the top. Where's this maximum value? 40 dB. Okay, so problem here is that the peak gain is 40 dB. 40 dB is 100 volt per volt, isn't it? Right? So here's what I'm going to do. I don't like that. I'm going to go back. What am I?
Why do we want to normalize it?
It normally is so that we normalize, get it? But things like Butterworth filters, they're defined as having the peak gain as 1. Also, that means you don't have any actual gain, everything is attenuation.
Okay.
But what I'm about to show you will apply, I'm just showing you how to normalize it now. Let me go back to MATLAB, and my numerator is 0.01 times the old numerator. That work? Why did I multiply it by 0.01? Because the gain for that frequency response was 40 dB higher than I wanted. I want to drop it down by 40 dB. 0.01 is negative 40 dB. So let's see. I'm going to hit the up arrow, frequency, see? Okay, there we go. That work? Good.
So,
I could have been sarcastic, Connor, and said, because the first problem on the exam says normalize frequency response, so you want to normalize the frequency response. Okay. Low pass filter. Oh, the other thing is, when you're comparing responses, to have one response way up here and the other one way down here, hard to compare their shape when they're at different levels, and all it takes is a constant to normalize them like that. Okay, and the way we get it, we wanted it at 0 dB. It was at 40 dB. 40 dB is 100, so multiply by 1 over 100. Excuse me. Okay? Yeah.
Yeah, that's still separate from the K value, right?
Oh, that is by K value.
But the normalization constant is different, because the K, we use K was 1,
I
right?
used K as 1. I changed K to 0.01 as
Okay,
well.
so we did change it.
Yes, I did. Except that's not, I didn't keep it out separate. I just multiplied the numerator by 0.01 all the way through. You look like you got a question.
No, I think I understand.
Okay,
I mean, you just change K to 1
That's
over 100.
that's right. To get rid of that gain.
so K is equal 1 divided by 100.
Yep. Because it had a gain 100 times bigger than I wanted.
Okay, so you just try to make it slower again.
Yep. Trying to drop it down to where it's the peak gain is 0 dB.
Why we drop now? Because it's too big, so we need. What is the reason we want?
Yeah, that's what he was asking. That's just something we commonly do, for one thing, so that we can compare different filters. So if you're looking at the response of two different filters and you're saying which one's a better low-pass filter, for example, if one of them is like that and the other one's way down here like this, we'll normalize them so that they start at the same point. And that point's usually 0 dB. Or you could just say it's something fun to do. But normally it is, so we can stretch this one up here and compare it to that one, and they're on the same, roughly on the same scale.
Okay.
Okay?
Yes, sir.
So, all right, there's how we do that. But I'm gonna turn the projector off for a couple of minutes and erase the screen. But notice I'm not erasing anything on MATLAB. We're going to get back to it in a couple of minutes. So, I confirmed this is a low-pass filter. And it's a fairly decent low-pass filter. It has all real poles and zeros and only second order. But here's what I'm interested in. Let's say that we input to that, x of n is, okay, so now k was 0.01, and I want to keep that. X of n is 1.5 plus 4 cosine of 0.1 pi n plus 8 cosine of 0.75 pi n. Okay, I'm going to input that to the system. And shortly, I'm going to do some calculations with MATLAB, and then I'm going to ask you, why did I do those calculations? Okay, so let's just identify first the frequencies in x of n, in the input. What are they? 0.1 pi? What else?
755.
Okay, what else?
0.
0
Yes.
or DC?
Yes.
Okay, good. I'm good with that. So, I'm going to introduce you to a command, and this command is called polyval. And it stands for polynomial evaluate in MATLAB. And let's say P comma Z. Okay, P is your polynomial coefficients, and Z is your value of your variable. Is this the first time any of you have seen this command? Okay, turns out to be a very, very useful command for what we're going to do. And so I'm going to write over here h of z, and the reason I'm writing it over here is because I'm about to lower the screen again. K is 0.01, that's already done, and then I'll have z squared plus z over z squared minus 1.7z plus 0.72. Okay, there is my, and the frequencies are DC, 0.1 pi, and 0.75 pi. All right. Now, I want you all to watch what I do, and you will see as I do these calculations, I'm going to use the polyval command, and you will see what I'm doing at each step, I think. So, my Z1 is e to the power j times 0. And the answer, what? No, I did the command wrong. EXP, j times 0. And you won't be surprised that the answer is 1. Just as you said it, I realized. Come on. On. shortly. So tell me, you see the transfer function over there is written in terms of z? Okay, so I'm going to convert my frequencies into z's. The first frequency was 0. C is e to the j omega. So the first value is e to the j0, which is 1. Okay? And by the way, is that where a frequency of 0 is? Right up there on the unit circle on the real axis. 1. I'm going to define my next one, z2, as exp j times 0.1 times pi. And it is that. Does that look reasonably close? 0.95 plus j 0.309.
What is that doing for us, that function, the z1 exp?
exp, yeah. exp parentheses j times 0, exp parentheses j times 0.1 times pi. Let me see if I can't blow this display up just a little bit. Where do we... I don't want to mess with a font on the screen, but there is somewhere that I can make this a little bit bigger, I think. Anybody see it on the screen here?